at some problems with tension. Here's an example. A purse has a weight of 8 newtons and is hanging from rest from a hook from its strap. What's the tension in the strap? Okay, so if we look at the forces on the purse, I'm going to draw a little free body diagram up here. We've got its weight, mg, and we know that the weight is 8 newtons. We've also got two tension forces, one that goes up at 60 degrees to the right, one that goes up at 60 degrees to the left. So if I look at what they look like on this diagram, we would have tension here and tension here. Everything's symmetric, same angles, same everything, so these tensions must be the same. I'm going to draw them both on my free body diagram starting from this point. So I'm going to draw the one on the left that goes up to the right. Oh, I want a skinnier pen. I'm going to draw that like, that's not a skinnier pen. Come on. I'm going to draw that up to the right, T, and I'm going to draw the other one up to the left. Sorry about writing over the words. What I have to do now is consider the fact that these two tensions are vertical and horizontal. So I need to split them into horizontal components. I'll call this Tx, and vertical, Ty. Over here I've also got Tx and Ty. If I look at the net force in the vertical direction, the net force in y equals m times ay. I've got three forces in the vertical direction. I've got Ty here, I've got Ty here, and I've got gravity pulling down. So I have Ty plus Ty minus mg equals the acceleration, which is 0. It's hanging at rest. So I'm going to combine those, add mg to both sides. 2Ty equals mg, which is 8 newtons. So divide by 2, Ty equals 4 newtons. Now, I'm going to just look at this triangle. I've been told from this diagram that this angle is 60 degrees, and the same thing on this side. So if I draw this triangle over here, I've got Ty equals 4 newtons. This is 60 degrees. I want to know the tension. I want to know the hypotenuse of that triangle. So I'm going to say sine of 60 degrees equals Ty over T. Sorry about that. So T equals Ty over sine 60 degrees. That's a 60. And that equals, let me find my calculator, 4 divided by sine 60, let's make sure we're in degrees mode, 4.62. Notice we didn't look at the Tx's at all. If we can do that too. We can say the net force in the x direction is ma sub x. So we've got Tx, and they're both going opposite directions. So the net force is Tx minus Tx, and that equals the acceleration, which is 0. So all this tells us is Tx equals Tx. It didn't really help us solve the problem in this particular case. Okay, another example, very much like this. we have a tree, a tree is knocked over in a storm and lands on a power line midway between the two poles that are 10 meters apart. If the tree exerts a downward force of 1.5 kilonewtons on the line that depresses the center by 0.5 meter, what is the tension in the line? So I'm going to draw my two poles. They are 10 meters apart. Now the line would normally just go across, but it's being pulled down by this tree and stretched downward. This distance here that it's stretched down by is 0.5 meters. And since the full distance across is 10 meters, if I'm just looking at the top here, half of that is 5 meters. I want to find this angle, theta. So I'm going to say, let's see, that would be tangent of theta is 0.5 meters over 5 meters. So theta is going to be inverse tangent of 0.5 over 5, and that is 5.71 degrees. Notice I've exaggerated it in this triangle. It's really much smaller than the way I've drawn it, but I exaggerated so you could see what was going on. Now let's look at the free body diagram. We've got the free body diagram of this little piece of the wire. We've got the force of the tree pulling down, mass of the tree times g. And then we've got tension this way, tension that way. Each of these has Tx and Ty, and that's T. We're looking for, I didn't draw that very symmetrically, maybe like that. We're looking for T, the hypotenuse, Tx, Ty. Remember in the last problem when we looked at the net force in the x direction, that didn't really help us? We're just going to look at the y this time. We've got Ty plus Ty minus mass of the tree times g equals the acceleration, which is 0. So Ty, just like the last problem, is going to be the weight divided by 2, which is, this is 1.5 kilonewtons. So this is 1,500 newtons divided by 2, or Ty is 750 newtons. You could have left it in kilonewtons too. It would have worked out okay. So now I know, because this triangle and this triangle are similar triangles, this angle is 5.71 degrees. So I'm trying to find T. Just like before, sine of theta equals Ty over T. So T is Ty over sine of 5.71 degrees. And that gives us, let's see, 750 divided by sine 5.71. 7,538 newtons. Should probably round it off. I'm only given 2 sig figs, so it becomes 7,500 newtons. Notice this, the tension in the wire is 10 times as big as the tension in the y direction. That's because this is such a tiny angle. Mostly, so we know that Tx is going to be very big. The two wires are pulling against each other, with a lot of force and only pulling up with a little bit of force. Next, this is a funny one. There's a picture of it in your book and in your packet. I'll try to draw one. Okay, a clown weighs 890 newtons. The coefficient of static friction between the clown's feet and the floor is 0.53. He pulls vertically down on the rope that passes around 3 pulleys and is tied to his feet. What's the minimum pulling force that the clown must exert to yank his feet out from under himself? So, we've got our clown. Oh, his feet are together because they're tied together. So they're just together. But he does have nice big clown feet. And he's happy. He's holding a rope over his head. Let's draw the rope in black. It goes up over a pulley, around another pulley. And then it's tied to his, we're tying it to his ankles. So these are the pulleys here, here, and here. If he pulls up on the rope is also pulling down on him. That's Newton's third law. So that tension is going to pull up on him. It's also going to pull his feet to the left. Friction is going to tend to pull his feet to the right. So let's draw a free body diagram of our clown friend. I'll draw it down here. We've got his weight, mg. There's normal force from the floor. There's tension as he pulls that rope. Tension's also pulling this way. That's the same tension. And then there's friction here, F, and that's our static friction. When it gets to the point just before he slips, that's when we have the maximum friction, and that's going to be mu static times N. So now we've got a lot of forces and we have to look at X and Y. So the net force in Y equals mass times acceleration in Y. He's got tension plus normal force minus mg equals, his acceleration is 0. So this equals 0. Now, I'm going to solve for the normal force. I'm going to move everything else over there. N equals mg minus the tension. That's a T. Now I'm going to look at the forces in X. In X we've got friction minus tension equals the acceleration. Just before he starts slipping, this is 0. So just when he's in equilibrium, just before he starts slipping, friction equals the tension. And the friction is mu static times normal force. That equals tension. And I solved for the normal force up here. I'm going to take this and substitute that in for the normal force. So I'm going to say mu static times mg minus t equals t. I want to find the tension. So I'm going to first multiply this out and then combine like terms. So I've got mu static mg minus mu static times t equals t. So mu static mg, I'm adding this term to both sides, equals t times 1 plus mu static. Divide by this part, t equals mu static mg divided by 1 plus mu static. And let's plug that in. Mu static is 0.53 times, the weight is 890 newtons, divided by 1.53 gives us 308. Okay, we have one last problem. This one says, a cable is lifting a construction worker and a crate. The weights of the worker and crate are 965 newtons and 1510 newtons respectively. The acceleration of the cable is 0.62 meters per second squared upward. What's the tension in the cable below the worker? So if I'm going to draw this in a funny way. I think it's easier to see what's going on, and it's funny. So I'm going to draw the worker holding on to that cable and kind of just hanging here. He's happy though. So that's the top cable. This one up here, I'll call it the tension above. And then we've got another cable here. The tension in that, I'll call it the tension below the worker. And then we're going to have the crate at the bottom. So we want to know the T sub B. Let's look at the forces on the crate. If this is the crate, I'm going to put a C there. We've got the force down, mass of the crate times G, and the force up is T sub B. Those are the only two forces on the crate. And we know that it's accelerating upward. A is 0.62 meters per second squared. So then if we look at we don't have any forces in the horizontal direction. So I'm just looking at the forces in the vertical direction. We've got on this side TB up minus mass of the crate times G equals, again this is mass of the crate times A. So I want to know the tension. I'm going to add mg to both sides. T sub B is going to be mass of the crate times A plus mass of the crate times G. Now what's the mass of the crate? We're given the weight of the crate, so we know mass of the crate times G is 1510 newtons. So to find just the mass, I would divide both sides by G, which is 10. So the mass of the crate is 151 kilograms. So this is 151 kilograms times the acceleration 0.62 meters per second squared, plus mg, we're given here 1510 newtons. So I'm going to plug that in my calculator. And I'm getting 16, let's see, I need 3 sig figs, 1600 newtons. Now we want to know the tension above the worker. So we want TA. There's two ways to think about that. We could look at the free body diagram of just the guy, or we could think of the guy and the crate as one system. I'm going to look at the free body diagram of the guy. We've got, well, I'll scoot that over. The forces on the guy, we've got TA, we've got the mass, what do we call him, of the worker, times G, and we've got TB pulling down. So I can say TA minus mass of the worker times G minus TB equals mass of the worker times A. So TA equals mass of the worker times A plus mass of the worker times G plus TB. And that's going to be the mass of the worker is going to be his weight divided by 10, 96.5, not going to put units here, times 0.62, plus his weight in newtons is 965 newtons, plus TB is 1600 newtons. So 1600 plus 965 plus 96.5 times 0.62 gives us 2630. And I dropped my pen. Newtons.